on an overview of optimization applications in Excel using our advanced products. My name is Dr. Sima Maliki. I am consulting lead and modeling specialist at Frontline Solvers. Just before starting, I want to make sure you're able to see my the PowerPoint slides, and also you can hear me. I would really appreciate if you type in the chat box if you can hear me. Dr. Klee, can you please confirm if you can hear me? Thank you very much. Okay, perfect. Let's start. So during the presentation, if you have any questions or comments, you can use the chat box, type them there, and at the end we try to respond to all of them as time allows. I strive to remain within the promised time frame here to thoroughly cover all the material. Sometimes it takes a few minutes longer. I very much appreciate your cooperation. As we all know, the optimization applications are widely used across many industries and functional areas. We'd like you to know that many of our customers have found optimal solutions for their industrial problems worth millions in savings, as building a model can give you insights and a money-saving optimal solution. Today, we explore how optimization can benefit you in solving your business problem and how easy it is to use our tools to solve them. Together, we'll review typical applications in transportation, inventory management, financial services, scheduling staff, and one example of automating optimization using VBA. Maybe you wonder what solvers are good for. So let's start talking about the decision-making process and using optimization to solve a problem. It is always best and most powerful to efficiently allocate scarce resources arising in your business. It can be your money, equipment, staff time, transportation fleet, or raw materials inventory. All of these are resources and they are allocated for some purpose. Deciding on which products to ship from factories to warehouses along each route is an allocation of products to routes. Portfolio optimization, it is allocating money to stocks in a portfolio, and scheduling is really a matter of allocating people to time slots or scheduling the availability of hospital operating rooms. Solvers or optimizers are software tools that help you determine the best way to allocate those resources. What do you need to use a solver, and how do you define your optimization model? Let's drill down on this further. There are three main steps. They are determining your decision variables, objective function, and constraints. So each optimization problem involves one or more decisions that must be made in order to solve the problem. The decision variables are typically numbers, reflecting how much of some scarce resource is being allocated to some use or purpose, and that is normally under your control. These decisions need to be made in the best possible way while simultaneously satisfying a number of logical conditions or constraints. Constraints reflect the physical situations, and there are various types of these constraints. Some of them represent limits on available resources, such as inventory or money. There are constraints that reflect the physical situation. One of them is non-negativity on variables. You can produce a negative number of products. You cannot assign a negative number of people to tasks. And some constraints are determined by policies that you or your organization may set. For example, in a portfolio optimization, you might have a limit on the maximum percentage of funds to be invested in any one stock or one industry group. And then you might have balance constraints. For example, warehouses are temporary holding points. Therefore, flow out from one warehouse is equal to its flow in. And these type of constraints have an equality form. We will look at some examples. Another common element in each optimization problem is the existence of some goal or objective that the decision maker considers when deciding which course of action is best. You can determine objective function by asking what measures are we trying to optimize. The best or optimal solution might mean maximizing profits, minimizing costs, or achieving the best possible quality. Now it is time to dive in and see how we can actually solve a problem in practice. Transportation and logistics operations of your company can be a competitive differentiator. So let's find out in this example how optimization can be used to optimize a transportation operation. This is about a company that has 3 different goods that have to be shipped from 2 factories to 4 warehouses, and from those warehouses to the 5 customers, or even directly from factories to customers with minimum cost. This is, at the right side, you can see a diagram of the system with nodes for factories, warehouses, and customers. Now we need to show the supply-demand pairs displaying feasible routes for the shipment plan. So these gold color arrows show the potential flows from factories to warehouses and customers, and then green arrows show the potential flows from warehouses to customers. The amount of products that is going to be shipped on each of these routes is under your control. So these are your decision variables, and we will reserve 1 cell for each of them in the worksheet, as you will see in a second. So let's take a look at the workbook. This is full analytic solver platform ribbon, which includes Excel Miner platform, and also includes simulation, optimization, and Excel Miner includes data mining, text mining, and forecasting. Today we are going to focus only the optimization component, so I want to show you how you can change the product, and you can do this when you have a trial version of our products. Click on Help, and then the first option is Change Product. So now instead of Analytics Solver Platform, let's choose Premium Solver Platform and click OK. Now we only have access to optimization components. Let's skim through the ribbon together. You can see that clicking on this Model tab displays or hides this task pane at the right side. In the Model drop-down, there are additional options for multidimensional modeling, and if you're interested, you can find some information in our user guide. Here in the Optimization Model tab, you can define your optimization model component, including your decision variables, constraints, and objective, and we will practice using them today. Then we have parameters. This provides you with the options to run multiple parameterized optimizations. Then we have Solve Action tab. Here you can just solve your optimization problem by clicking on this light bulb, or the additional options for you. Then in the Analysis tab, you can analyze the results, create different reports and charts. Tools tab enables you to create, examine your optimization results, and then this Publish button allows you to publish your models for use and distribution on the web. For example, Excel Online and Google Sheets. And then Get Data. Get Data allows you to summarize from big data. You can bring in your input parameter data that you would use to drive an optimization model. For example, if you have millions and millions of sales orders in a large database across different hard disks, you are not going to use every single order in your optimization model. With this facility, you can get a sum or average or even a sample based on region or gender. Now let's explore the Help tab. Here you can display online help, use live chat, control guided mode, which we will discuss in more detail today. Then open examples and online tutorials and access user and reference guides. And also you can see your license status and more. Now the task pane. Model tab allows you to view your model elements and also you can edit model elements in place. Then we have Platform tab. Here you can view or change the platform options, such as, like the first one is number of optimization to run, or default bounds or your decision variables. Then you have Engine tab. Here you can select a solver engine and then you can set its options. Then Output tab allows you to view a log of solution messages or a chart of objective value. Now let's click on Model tab so we can see the optimization model components and we can review our example together. So as you can see in this Excel workbook, the cost of shipping from factories to warehouses, factories to customers directly, and from warehouses to customers are recorded in these cells. These are inputs to the problem that are not under our control. These shipping costs are quoted to us by our outside shipping company, for example. What is under our control are decisions about how much to ship along each route at these different locations. So here we need to reserve cells for variables representing quantity shipped from factories to warehouses, factories to customers directly, and from warehouses to customers. This is how we define decision variables in Excel using our tools. And as you can see, if I click here, you can see the variables here. Under variables, we have 3 groups of decision variables. So we have reserved these cells and then we have defined them as decision variables, and we will practice defining an optimization model from scratch together after this example. What measure are we trying to optimize? Each route of flow incurs a cost. So there are 2 goals that need to be carefully addressed in this problem: total costs and the service. We want to provide the service with minimum cost and ensure that each customer demand is completely satisfied. So the objective function is minimization of total cost of shipment along all the routes. So you can see in the Model tab, you can see the objective is total cost and it should be minimized. Now let's double click and see which cell. If the cell is C91, that includes the formula of that objective. So let's scroll down to cell C91. As you can see, it is represented by some pair of functions. Let's look at the first component of this objective function, which represents total cost of shipping. To calculate total cost of shipping from factories to warehouses, since the cost coefficient for these routes are defined in cells C10 through F15, we need to multiply these by total amount of product that will be determined to be shipped, our decision variables, for which we have reserved cells C41 through F46. And similarly, we need to add the other costs. Now let's take a look at the constraints. What restrictions limit our choice of decision variables? The capacity of each warehouse, supplies available from each factory, and the demand from each customer need to be considered. So you can see the constraints in the Model tab. So let's take a look at the first one. These are warehouse capacity constraints. We want to make sure what we ship into the warehouses doesn't exceed the capacity of those warehouses. We cannot overload warehouses, as like each one has a physical capacity. So we have total shipped to warehouses should be less than warehouse capacity, and these are just numbers input to the model. And here we are calculating the totals that are shipped to each. Actually, this is not the location. So this is for row 47. So let me actually show you. So we have just sum of all the product that is shipped to that specific warehouse 1. And then it should be less than 35,000, the capacity of that warehouse. Now the second one. So we have a certain supply available at each factory, and that is provided in these cells, age 63 through age 68. For example, the total flow out of factory 1 for each product type must be smaller than or equal to the factory supply. So total from factory should be less than factory supply. You can see you can define blocks of constraints. You don't need to add them one by one. Again, this is a sum from factory 1 for product 1. Okay. Now we need to ensure that each customer product demand is satisfied. So we have total to customers should be greater than our demand. And then warehouses are temporary holding points. Therefore, flow out from one warehouse is equal to its flowing. These type of constraints are called balance constraints. As you can see, they have an equality form. So total 2 warehouses should be equal to total from warehouses. And this, we just calculate the sum and then define the constraints. And you will see in a minute after this example how we define constraints. Now we are ready to go ahead and solve the model by clicking the Optimize button on the ribbon. So I'm just clicking on this light bulb. This time, we are going to step our way through guided mode and see what it can tell us. This feature is a guide offering help for you in each step of your modeling efforts, preventing common errors. Let's click on Continue. 2 things happen here. First, as you can see, Solver has analyzed all the formulas in this model and determined the structure of our model automatically. This is diagnosed as an LP convex or linear programming convex model. Because the right solver engine wasn't selected, it is letting us know and giving us other choices. So the LSGRG was selected, which is a suitable solver for nonlinear problems, but the best solver is LP quadratic. So let's choose that one. And the engine that is offered, and then click on Next Step. Here, guided mode tells us that Solver found the solution, all constraints and optimality conditions are satisfied. Now let's click OK. We are back where we were without the guided mode. And you can see that output report, you can see log of solution messages, what engine was used, and how much did it take to solve this problem. So here is the solution. We achieved what we wanted here, which was to determine how best to ship products between the factories, warehouses, and customers. So to minimize our shipping cost, which is now $519,700. Now, after you have used this guided mode for a while and you're solving over and over, you might want to get rid of this dialogues that you have to click through every time. To make this change, you can just click on Help and then Operating Mode. Instead of going, so you can see there are 3 options. Instead of going to Expert Mode, which eliminates the help, you have another choice, Auto Help Mode, and which will only bring up the dialogues when there is a problem. I'm going to keep the guided mode for now, but that's how you can change it if you want to get rid of it. We just looked at how optimization can help us with a typical transportation problem. Now let's briefly look at an inventory management example before building the optimization model from scratch. So this is about a warehouse that sells 4 products with a different demand for each product. Each product has a different holding cost and requires a certain amount of space. We have a limited storage capacity, so the problem is, what is the best ordering policy for a warehouse to minimize costs while meeting demands? As you might know, there is an analytical solution for this problem, which is known as economic order quantity, EOQ. Unfortunately, this formula doesn't always work in real world. Demand usually fluctuates, ordering time is variable, and other factors arise to further complicate this problem. And in this model, we have one such factor, a limited storage space. So as you can see, the variables are defined as quantities, amounts to order each month for each product. And we can use the name ranges for this block of variable. And then we have constraint space used should be less than or equal to available space. And then our objective is to minimize total costs. So let me actually show you the formula of objective. So we have total cost, that is the sum over all products cost. And if you look at one of the formulas, you can see that this is calculated by individual cost of each product, and then this is the formula. Holding cost times average inventory level plus the cost to place an order times average number of orders. Now, this is a nonlinear problem. Let's click on Optimize and verify this information. So we use guided mode, click on Continue. Here it is telling us that this model was diagnosed as nonlinear programming non-convex model. Let's click on Next Step, and here are the results. So these are the amounts to order each month, minimizing cost, meeting demand, and without exceeding storage space. Now, our next example is a financial services application. It is about allocating money to stocks, and we are defining the optimization together. An investor wants to target a specific rate of return for his portfolio while minimizing risk. So this is a portfolio optimization application, and the goal is to find the best combination of stocks that minimizes risk for a given return. Let me open the workbook. So I've just recorded the data. You will see there is no optimization model defined in the Model tab of Task pane. You see under Variables or Constraints, there is no components defined. And let me increase the size. As you can see, returns, variances, and covariances between all stocks are known, and I've just recorded them here. So in this problem, the variables are the percentage allocations of funds that we can invest in each stock. So let's first start with defining decision variables using the ribbon. So for these percentage allocations of funds, I have reserved these cells, C14 through G14. And the only thing is I've entered 0% in each of them, just a value. Now, I'm going to reserve them to hold the percentage allocations of funds or decision variables. Let's select them first thing, and then click on Decisions, and then Normal. And I use a name range for this block of decision variables. I call it allocation. So now you can see that the decision variables allocations are added in the Model tab of Task pane. And this is how we define decision variables. Then the objective function for this portfolio optimization is the portfolio variance. So we have to calculate portfolio variance. And here I have done this in cell C18. I've entered this formula, quad product function. And this is just a custom function that you can use with our products. So we define this variance, we select it now. We just want to define objective function. So we select this cell that includes the formula of objective, and we want to minimize our variance, our portfolio variance. So select the cell, click on objective, and then the first one is minimize. You can see that portfolio variance is defined as an objective function, and it is a minimization type problem. Again, it's just a name range. I select the cell and gave a name to it. Now about the constraints. We have two constraints to define together. One is the total portfolio constraint, summing the allocations of funds to stocks, which is summing to 100% or 1. So we want to make sure the sum of all portfolios, sum of all allocations is equal to 1 or 100%. First, we need to define this sum over all allocations. So I have defined this sum function over C14 through G14. Now I want to define this as a constraint that this sum should be equal to 100% or 1. So this is how we do this. Select the cell. So you have entered the formula, select the cell that includes the formula, and then click on Constraints. Then first option, Constraint, and now let's choose equality sign, because we want to make sure it is exactly equal to 100%. Now this Add Constraint dialog appears. You can see this cell H14, I call it total portfolio. It is selected as the left-hand side of constraint. The right-hand side, we just can enter 100% or just 1. I would just enter 1 and click OK. Now you can see that total portfolio is added, the total portfolio constraint is added. Now we have a second constraint. We want to make sure that our total portfolio return is greater than 9.5%. So first thing is we have to calculate the total portfolio return. And then we add a constraint that it should be greater than or equal to 9.5%. So here in cell C20, I have calculated this. I've used this sum product of allocations and stock returns to calculate our total portfolio return. So this is the formula. Now I would select it and then click on constraints. And then again, we use constraints and then greater than or equal to sign, the last one. So we want to make sure this portfolio return or C20 is our left-hand side of constraint, and in the right-hand side, we would enter 9.5%. Let me clear OK. Now you can see that portfolio return constraint is added in the model tab of task pane. Okay, we are ready to solve this optimization problem. And let's click on optimize. I am going to, let's click on continue and see. This is a quadratic programming convex type model. Click on next step, and then here are the results. So this is the allocations of funds to different stocks, resulting in minimum risk or minimum variance portfolio that achieves 9.5% return. This is often called an efficient portfolio. You may have heard of the efficient frontier. Using Premium Solver, we can construct that efficient frontier rather easily. And let me show you how. So by the way, here you can see that the total portfolio is equal to 100% as we just requested in this constraint. And total portfolio return is 9.5%, which is greater than or equal to the 9.5% return that we requested. So far, in our example, we have used the solver and found the optimal portfolio with minimum variance for a given target rate of return of 9.5%. Let's generalize that. We can utilize parametric optimization to find the efficient frontier that is the optimal solution for several levels of portfolio return. To do this, first you have to choose an empty cell. So I'm going to choose D20. Let me color it so we don't forget. So it's D20. This is an empty cell. And then let's click on Premium Solver Platform ribbon, click on Parameters, and then Optimization. So what I'm trying to do is to define a parametric return rate. Instead of 9.5, I want to check the an interval, between 8% to 14% for my portfolio return rate. And then I want to run different optimization. So for the lower level, I'm going to enter 8% for this parameter, and for the upper level, I would enter 14%. And that's because one of the last stock is actually returning 14%. Okay, let's click OK. And you can see that this D20, our parameter is added under parameter section of this optimization problem. Now, we need to modify our constraints right-hand side to point to our parametric return rate instead of that single value 9.5%. So this is how we can modify a constraint. We can double click it. The add constraint dialog appears. Now I would select this button and point to D20. So you can see D20 is now the right-hand side, our parametric return rate. And click OK. So our constraint is modified. The only thing that is left we need to do is to change the number of optimization to run. Let's click on Platform tab. As you recall, the first option is number of optimization to run. I'm going to change it to 10. Okay, we are ready to solve the problem. Just before that, I'm going to clear the output with this button so you can see the output of 10 optimization problem. Let's click on Optimize. I'm going to skip guidance. And if you scroll up, you can see that optimization 1 through 10 just finished. We finished 10 optimization. And now in the worksheet, you can initially see values for the last optimization, perform optimization number 10. But using this optimization number in the ribbon, you can look at any of the optimization results, for example, optimization 1, and you can see the values for your decision variables, objective, and return. Optimization 3, and you can see the values, so on. So you can see the optimal values. Now, let's click on charts, multiple optimizations, and then let's choose monitored cells. I'm going to choose the objective portfolio variance, click on this second button to move it to the right side and click OK. This is the efficient frontier plot. You can see the optimization index, optimization 1, 2, 3 through 10, and this is the optimization, the portfolio variance on the Y axis. Now you can click on this right pane button. As you can see, I can open this other chart options, and then let's go to chart options. Okay, for X coordinate, we have two options, either optimization index or the other one is optimization, the parameter value. So let's select that one. So instead of the optimization number, now we can see the return threshold on the X coordinate. Okay, let's close this and go back to our slides. Just a recap on what we practice: modeling and solving problems in Excel spreadsheets. So you just need to reserve a cell to hold the values of your decision variables. Then pick a cell to represent the objective function, enter the formula that calculates your objective function in that cell, and then define it as objective. Then pick other cells and use them to enter formulas that calculate your constraints left-hand side. And then for your right-hand side, you can enter numbers, you can refer to other cells, or even directly in that Add Constraint dialog. And one quick note is that it is best practice to use constants for constraint right-hand side. So anything that depends on your decision variables, it is better that you move it to left-hand side, and in the right-hand side have a constant. Now, let's look at some scheduling examples. This is about allocating your staff. So this is about an amusement park that needs a certain number of employees each day of the week. And then every employee must be on a schedule that gives him or her 2 consecutive days off. How many employees should the park hire, and what schedule should they be on to minimize total payroll costs? So let me open the workbook and review the rest of the example together in the workbook. And let's increase the size. So for employees working 5 consecutive days with 2 days off, we are looking to find a schedule which meets demand from attendance levels while minimizing payroll costs. We have 7 such schedules. So these are the days off, the 7 possible schedule A through G that have 2 days, consecutive days off. Now we have defined the employees per schedule. These are our number of employees that we need to hire for each of the 7 possible schedules. And as you can see, we have defined this as integer variables. And the way to define variables as integers is that you first define them as your decision variables, then go to constraints, variable type bounds, and then here you can define the variables as your integer variables or binary or any other types that you need. And this is the same way when you want to define lower and upper bound for your decision variable. Just select them after defining them and then use that option. So we have the constraint, employees per day should be greater than in the required employees or our demand. And then our objective is to minimize payroll costs. So let's see, this is the way we calculate the payroll. Now let's solve this problem. optimize. I'm going to skip guidance, and here are the results. The number of required people for each schedule. Now, in the next workbook is another version of this problem. Imagine this park has hired the required employees. It now needs to decide which employees go on which schedule. So they have asked employees, and each employee has given a list. Each employee has given a list with his or her preferences. S7, let me increase the size. So these are the schedules, these are the employees, and these are their preferences for each schedule. S7 means the most desired schedule. For example, schedule F is the most desired for employee 1, and then a 1 means the least desired. How should the park divide the schedules among the employees? So this is how we have solved this problem. We have defined this binary variable, so this whole block of decision variables, one variable for each schedule to be assigned to each employee. And these are defined as binary. So if it's 1, if you get 1 here, means schedule A is assigned to employee 1. So you can see schedules are this block of decision variables, and then all of the schedules are defined as binary, so they can either take the value of 1 or 0. Now we have to make sure each employee is only assigned to one of the schedules. So we calculate this sum over all the schedules assigned to employee 1, and then we have the sum for all of the employees, and then you can see that this whole block is selected and it is defined to be equal to 1. So we want to make sure each employee is only assigned to one schedule, or allocated to one schedule. And then we want to make sure employee scheduled is equal to the required employees. And for this one, we are summing over each schedule. So we need 3 people for schedule A, and so we want to make sure the sum over a schedule A assigned to employees 1 through 25, the total should be equal to 3. And then so on for schedule B through G. And now let's look at the objective. So our objective is to maximize the total preferences, or to optimize employee preferences. And we want to maximize that. So it is in cell U50. And let's look at the formula. So it is the sum of all preferences for all the employees. And if we look at each preference, it is the sum product of the employee's preferences and the schedule that is assigned to that employee. Okay, so this is defined to be maximized. Now we are ready. Let's click optimize and see the results. Let's skip guidance, and here are the results. So for example, you can see that for employee 3, it is schedule D is assigned to him, and this employee had the most desired. It was the most desired schedule for him. Okay, so in this model, we solved the problem after finding the optimal solution of scheduling 1. However, it is possible to find both solutions automatically. You can write a VBA macro to do this. So actually now it is a good time to talk about automating your optimization models. Automating your models allows you to run your predefined solver models and control the solver. You can automatically update data, run the model, and retrieve the results, and also create an application to distribute to your end users. And you can automate your models and control solver engines using VBA Object-Oriented API. Now we are going to look at the refinery example. The goal in this problem is to plan the operations of the refinery to maximize total profit. The VBA code for this model shows some of the many ways you can use the object-oriented API, such as how to call the solver and how to retrieve sensitivity information from VBA. So let me open the workbook. So this oil refinery purchases 2 crude oils, crude 1 and crude 2. Then these crude oils are put through 4 processes: distillation, reforming, cracking, and blending, to produce petrols and fuels which are then sold. Again, objective is to plan these operations to maximize our total profit. So you can see this is the objective. And you can see all the components of this model in this tab. So we have defined the optimization. Now we're just using the VBA to run this optimization and retrieve sensitivity information. So let's take a look at the code. I'm going to click on Developer tab, Visual Basic. First, with dim prob as new problem, we create an instance of the problem. I'm going to skip all the details. I will show you how to access this example. You can review it on your time, but here we just it's about the guided mode. We turn it off, and then we pick a solver engine, standard LP quadratic. Then we set its parameter, the engine parameter. And now with prop.solver.optimize, we run the optimization problem. Then in the next line, we are going to put a message box. You will see it as we run the model. And then below it, we have a for loop. Within that for loop, there is another message box. So there's another for loop, and there's another message box. And we're getting different final variable values, reduced costs, and shadow prices. Then below, you can see that we are asking, we have prop.solver report, and we are asking for an answer report. And you will see that happen as we run the model. So let's close this and click on this platform, and let's click on this to run the model. So we get the optimization status. I'm going to click through this quickly. So we get these are the message boxes, and then we get final variable values, and we get reduce cost as requested, and shadow prices. And you can see that finally the answer report is generated for us. Now let's talk about our different products. You can access our optimization software within Analytics Solver Platform or Risk Solver Platform products, or get it as a standalone program such as Premium Solver Platform or Premium Solver Pro. Everything we saw today can be done using Premium Solver Pro or more advanced products subject to your model size. The Solver Upgrade products have very nice usability features with limits related to problem size, structures, and solver engines. The platform products allow you to add 8 different large-scale plugin solver engines that you can use to extend the power of these products. These make it practical to solve very large problems, essentially only limited by memory. We have Groby, Express, Nitro, and so on. You can do much more with our product. We offer a complete solution for any type of conventional and stochastic optimization problems, simulation and risk analysis, decision trees and forecasting, text mining, and data mining. Furthermore, you can find optimal solutions for models with uncertainty using chance constraints, recursive decision variables, and robust optimization and stochastic programming methods. This wide-ranging product line empowers you to perform analytics on the web and desktop spreadsheets, also web, server, and desktop applications in any scale. As we mentioned earlier, many of our customers have found optimal solutions for their industrial problems worth millions in savings. We saw today how building a model can give you insights as well as a money-saving optimal solution. Frontline solvers offer powerful tools to help you get a better solution by automatically diagnosing your model structure, fixing problems for you, selecting the solver engine, and providing updated information at each step. For instance, one of these features was the guided mode that helped us choose the right engine. You might be asking, what is the next best step to begin? Okay, please register at our website for free. If you haven't done so, this will allow you to access our downloadable user guides, more than 40 example models like the ones we have been showing here today. Furthermore, it allows you to download a free trial at any time whenever you are ready. Try it yourself, go to example models, and you have full technical support during this trial period, and you can ask questions. Just give us a call. This is a specific number for this webinar attendees, and or use the live chat, send us email. So just before we start answering questions, let me show you how you can access all the examples. So when you install one of the products, click on Help, then click on Examples. Here you can see all the example models, but either you want to look at this part, the optimization examples, all of them are available here, or to see the ones that I showed today, click on optimization. And then, for example, I used logistic example. Transport 3 was the transportation problem we looked at together. And then another resources would be to go to our user guides and click on main user guide. And then there are different chapters on optimization. It's about even simple, starting from a simple example, there are more advanced chapters on mastering optimization concepts and also how to build larger scale models. And also there is a chapter on automating your optimization in VBA. And another resource I wanted to show you is our YouTube channel. And so it is youtube.com user frontline solvers, and I'm going to share it with all of you in the chat box. So YouTube. And here you can find in playlist various videos from just simple examples looking at a feature to different more advanced videos on, for example, stochastic optimization. If you need to learn more, this is one playlist that can help you with that. Thank you very much. If you have any questions and comments, please type them in the chat box. Also, please remember you're always welcome to send any questions or comments to consulting@solver.com, and I will be in contact with you. I'm sharing my email address with all of you to create a support ticket in our Zendesk system, and then we can help you. So if you have any questions, please type them in the chat box. Thank you very much. I really enjoyed presenting this webinar and trust that it was helpful to you. Again, you're always welcome to send me any questions or comments. If you have any questions, I'm happy to answer them. Thank you. Okay, we look forward to future webinars with you. We appreciate your time, and bye for now.